This section, we're going to talk about variation and applications. So the objectives are, we're going to find the equations of direct, inverse, and combined variation given values of the variables. We're going to solve applied problems involving variation. The direct variation, if a situation gives rise to a linear function, so we have this f of x is equal to kx, or y, because we know that f of x is equal to y, so we can say, well, y equals kx, where k is a positive constant. We say that we have a direct variation, or that y varies directly as x. Or we can say y is directly proportional to x, and the number k is called a variation constant, or it can also be called a constant of proportionality. Okay. So the direct variation. The graph of a direct variation where we have y equals kx, where k is greater than 0, it always goes through the origin and rises from left to right. As x increases, y increases. That is, the function is increasing on the interval of 0 to infinity. The constant k is also the slope of the line. So here's a good diagram of one. Example 1, we're going to find the variation constant and an equation of the variation in which y varies directly as x. So we're going to say y is equal to 32 and x is equal to 2 in this one. So we're going to take we got our order pair. I said y is equal to 32, x is equal to 2. We're going to take our formula, our function here, y equals kx, and we're going to plug in what we know for y and x. So we put in 32 for y. I got k times that 2, which is my x. Now we're looking for k, right? And I got this 32 is equal to 2k. You could have had it k2. Either way it goes, it doesn't matter. In multiplication, 2 times 3 is 6, and then 3 times 2 is 6. So that order doesn't matter. However, I want the positive 1 coefficient on k, and I got this 2. So I'm going to divide by 2 because division undoes multiplication. Now I got k is equal to 32 halves, which reduces down to 16. So my constant here, my variation constant, is 16 when we have a y value of 32 and an x value of 2. We can rewrite this as, in the model form, y equals 16x. Our second example, water from a melting snow. The number of centimeters of water, and we're going to call it capital W, will produce from melting snow varies directly as S. So we're going to let S be our snow, and of the numbers of centimeters of snow. Meteorologists have found that under certain conditions, 150 centimeters of snow will melt to 16.8 centimeters of water. To how many centimeters of water will 200 centimeters of snow melt under the same conditions? So we're giving the information to use the capital W for water and capital S for snow. So that gives me this function here, right? So now what's going in the place of y is going to be capital W of S. And what's going in the place of x is just going to be S. And k is still my constant variation. So next, let's start solving for our equation. And whenever you do application problems, if you can draw charts or a picture, that would be your best interest because sometimes it makes it easier. So if we got this cylinder and filled it up with snow, and let's say, well, we're going to solve this. We fill it up with snow, and we got S centimeters of snow. And then we got, after it melted, we got W centimeters of water left. So now I can take this W of S, because they said if we need to, let's go back to the application problem. It said here that meteorologists have found that under certain conditions, 150 centimeters of snow will melt to 16.8. So let's put in the place of this capital S attached to the W, because that's the whole thing, right? That's the whole thing of snow. So we're going to say it's 150. Of course, this is not what we're needing. We need to find the constant K in order to find the 200 part. So we put in the place here. So now I got WS, or W of capital S, and in that place it's 150. And we can just rewrite it as 150 is equal to K times that 150. All right, so when I divide by this 150, oh, sorry, my apologies, guys. I just misspoke to you. Let's redo this. My W of S is going to be equal to that 16.8. That's my end result after it melted. My capital S is going to be the 150. This is the snow before it melted, okay? And then WS is after it melted. Now let's plug it in, right? So this becomes the 16.8, 150K. Let's divide by 150 because we want K by itself. So now I got K is equal to 16.8 divided by 150, which is approximately 0.112. So here's my variation constant. So now that I can rewrite this as this. Oops, we don't need another 0. Or we can also write it as Y equals. Sometimes that just makes it easier. It's just whatever works for you. Now, let's move on. I probably should have gave myself more room on the screen. I wrote too big. Okay, so now that I know this, we can go back to the application problem. The application problem said, now we want to determine how many centimeters will 200 centimeters of snow melt to. All right, so I got my constant K, right? It's 0.112. I got my equation here, and I'm going to come right here. It actually drawed it out. So let's do this. So now I'm going to go ahead and leave it as Y equals. The software or your textbook may have the WS, and you could leave that too. I'm going to plug in the place now for S because it's my snow, right? 200 centimeters. So now I got 0.112 times that 200. And when we multiply that out, now I get 22.4, right, centimeters. Again, this is this, which is this. It's approximately this. So my water is 22.4 centimeters. That's with 200 centimeters of snow before melting. There you go. Inverse variations. So inverse variations, if a situation gives rise to a function, we get f of x is equal to k divided by x. You know, the direct was k times x. Now it's divided, right? We can use the f of x, or we can use y because we know they are equal to each other. K is still a positive constant. We're going to say that we have an inverse variation, or that y varies inversely as x, or y is inversely proportional to x. A number k is called the variation constant, the constant of proportionality. So that did not change. For the graph of y equals k divided by x, where k does not equal 0, x increases while y decreases, which makes sense because now we got a division going on. That is, the function is decreasing at the interval of 0 to infinity. So inverse variations, the graph of an inverse, y equals f of x, or excuse me, y equals k divided by x. this is again still K does not equal 0, is like the one shown below here in this image here. Let me scroll down just a little bit so you can see it. Note that as X increases, Y decreases. Okay, so we have this function going on. It's decreasing at an interval 0 to infinity. Now let's do our example here. Our example says find the variation constant and an equation of the variation in which Y varies inversely as X. And we get Y is equal to 16 and we're given that X is equal to 0.3. Let's find the K constant. So we know what Y and X is, so let's just plug it in. So Y is 16 and K is over 0.3, which is X. To undo this division, I'm going to multiply, right? That becomes 1, leaves me with positive 1 for K. That means I got to do the same thing over here. So I got 0.3 times that 16 is equal to K. Now, when I'm done multiplying, let me finish this right here. We get K is equal to 4.8. So now I got my variation constant. I can turn around and write it as Y equals 4.8 over X. And now I got my equation. The next example says we're going to do a swimming pool. It says that the time T required to fill a swimming pool varies inversely as the rate of flow R of the water into the pool. A tank truck can fill a pool in 90 minutes at a rate of 1,000. We can say 1,500 is what I would like to say, and I got tongue-tied. Anyways, 1,500 liters per minute. How long would it take to fill the pool at a rate of 1,800 liters per minute? So we can express the amount of time it required as a function of the rate of flow. So that's where we get this function of T of R is equal to, and that's supposed to be an R, K divided by R. So what happens? T becomes my Y value and R becomes my X value. And it's just a notation of representing what each part means. K is still my constant and we're wanting to find it. So when we look for the K, we're going to plug in what we know. We know that it said that we had a rate, which is my R, of 1,500 liters per minute. So I'm going to call this R. And then we had 90 minutes to fill the pool. So that's going to be my time T. So let's plug it in. I got 90 is equal to 1,500 K. And now let's divide by the 1,500. And now I have K is equal to 90 divided by 1,500, which will give me, and I'm going to double check because it gave me such a big number, which makes sense, but let me double check. And it should have been a small number. So yeah, there we go. That was a small number. Oh, I apologize. I said divide. We are already in division form. I wrote the wrong formula down. Sorry. Let's fix this. We got 90 minutes is equal to 15 or K over 1,500. There we go. We're going to multiply because we're going to undo the fraction. So if you caught that, kudos to you. So now what I got, 90 times that 1,500. So it's going to be 135,000. It's my variation constant. So now I can come over here and write this in my equation. Okay. So now it said, the last part said, what does it want us to do now? Let's go to that page. It says next, we use the equation to find the time. Oh yeah, because we want to figure out what it asked for. It said, how long would it take to fill the pool at a rate of 1,800? So what do we got here? We got our T time of our rate is equal to K over the 1800. But we know what K is. We just solved it. It's 135,000 divided by the R, which is 1800. Let me clean up my writing right quick. There we go. Let's divide this out. Let's see what we get. So we get 75 minutes. So it takes 75 minutes to fill the pool, 1,800 liters per minute. So that's pretty good. About an hour and a half. Okay, there we go. We got it. Now let's go to, oh, here is that part that I was wanting to go to. Okay. Solving variation problems. We want to determine the direct variation or the inverse variation applies. Write the equation of the form of y equals k times x in a direct variation. Okay. If we're doing an inverse, we got k over x. So I would go when I was, I flipped it. I went from multiplication, division. You got to be careful. What are we solving for? If it's direct, it's k times x. If it's inverse, then we're going to have k divided by x, okay? And it's a very easy mistake to make, so don't feel too bad. Just catch it as you're going. So we're going to write the equation of the variation and use it to find the unknown. So we were doing that, right? Combined variations, other kinds of variations. So we have y varies directly as the nth power of x if there is some positive constant k such that y equals k x to the n. Y varies, so that's directly. So if you may need to write that down on a separate piece of paper, I would. Now the inversely, y varies inversely as nth power of x if there is some positive k constant where y equals k divided by x to the n power, okay? Now, y varies jointly as x and z if there is some positive constant k such that we get y equals k times x times z, okay? Example 5 says, find the equation of this variation in which y varies directly as a square of x and y is 12 and x is 2. So what we're going to do is just plug in what we know here. Y is 12. K times x squared, oh, 2 squared. Let me erase this. I was going to write x down. So be 2 for x and we're squaring it. Okay. So what do we get? We get 12 is equal to k times 4. I'm going to divide by my 4. And now I get k is equal to 3, which works out great because I'm going to plug it in. And now I get y is equal to 3x squared. Okay. So this was my directly. Okay, maybe I skipped one. Let's make sure I didn't. Oh, okay. All right, our next example, example 6 says, find the equation of variation in which y varies jointly as x and z and inversely as the square of y or w, and y equals 105 when x equals 3, z equals 20, and w equals 2. So what do we got here? It said that, so here's a clue. It says jointly, we got a variation, right? So what do I got? I got y is equal to k times xz, but it said inversely with w, and it's the square of w. So we're going to divide by the w. Now let's plug in everything we know and solve for k. So we know y is 105. Then we got k times z, which is 3 times, or excuse me, k times xz, and x is 3, z is 20, and then w is 2, and we're going to square it. So now I got 105 is equal to K times, I'm going to go ahead and leave it in this format just for now because 2 squared is 4. And I see 4 goes into itself once and it goes into 25 times. So I'm just going to save myself some extra work. Now I got 105 equals K. 3 times 5 is 15. And it's all over 1. So now let's divide by the 15. So now I have K is equal to 105 divided by 15. And let's see what that gives me. And that gives me 7. So my constant K is 7. And now let's write it in our equation. Whoops. Right. Let me give myself, I'm going to write it here at the top. So now I get Y is equal to 7xz divided by W squared. And that's all we need to do. All right. We got another example to work out. This is volume of a tree. The volume of wood V in a tree varies jointly as the height H and the square of the girth G. Girth is the distance around. If the volume of a redwood tree is 216 meters cubed, when the height is 30 meters, the girth is 1.5 meters. What is the height of the tree whose volume is 344 meters cubed and whose girth is 1.6 meters? So we're going to have to find the constant K. So let's go ahead and write everything out. We got the volume V, right? That's what we're solving for, the volume. So I got volume V, and it's going to be times the constant. It's going to be times the height and the girth, right? And it said the girth was squared. So now let's plug in what we know for everything. It said that we had a volume of 216 meters cubed and times or is equal to K times. It said the height is 30 meters and then the girth was 1.5. And we're going to square it. So let's clean this up right quick. Let's go ahead and square the 1.5, which gives me 2.25. And you may want to do it all in one step. It's all right if you did. All right, so now I got that times 30. Let me scroll down just a little. So that gives me 67.5 K is equal to 216. Let's divide by that 67.5. And now I have K is approximately equal to, so 216 divided by 67.5 is 3.2 meters. Okay, so we are talking in meters, but anyways, it's 3.2. This is my constant K. So now I can figure out the next part, right? So I'm going to take my volume, right? We have this. We don't know the height. That's what we're solving for. So let's plug in. So we got 2 options. You can plug in now and then solve for H, or you can just go ahead and say, oh, K and G squared is being multiplied to H. If I divide both sides by it, they reduce down, and now I have H is equal to volume over K G squared, and then we can plug in what we know. We got 344 for the volume. K is 3.2 times my girth, which is 1.6 squared. So now, whoops, now I am going to erase this right quick. I'm going to solve this. I got H is equal to, so let's do it. 344 divided by 3.2 times that 1.6 squared. I get, and we need to make sure and read the directions on what it wants you to round to. I'm going to just write what I get. This is what I got. So be sure and read where it wants you to round. And I was going to see if it said where to round. Oh, it rounds to the nearest whole number. So if you're going to round to the nearest whole number, or they could have rounded to the nearest tenths and it still bumped it up because of the 9. So just be sure and read. But I'm going to look at the number behind it. If it is greater than or equal to 5, all it has to be is yes to either one. We're going to add 1 and drop it off, right? So in this case, my height is 42. All right, and I'll just scroll down so you can see the directions and explanation right quick. All right, thank you.